Welcome to the Explainer, everyone. Today, we're diving headfirst into the absolute core concepts of Chapter 1, Fundamentals of Terrestrial Orbit and Celestial Navigation. We're going to break down the physical mechanics of our planet in a way that is clear, super testable, and honestly, just completely fascinating. Let's get into it.
Okay, here's our game plan for today. We've got four main sections to conquer. Section 1, the Earth's elliptical orbit. Section 2, the magic 23.5-degree tilt. Section 3, decoding twilight and horizons. And finally, Section 4, perfecting cosmic timekeeping.
All right, Section 1, the Earth's elliptical orbit. Let's start by looking at the big picture view of our planet's journey around the sun.
You might casually think a year is just 365 days, right? But to be highly precise for navigation, Earth actually takes exactly 365 days, 5 hours, 48 minutes, and 45 seconds to complete one oval-shaped or elliptical orbit. But before we get into the nitty-gritty mechanics of that orbit, here's a question straight out of your study materials. At what approximate date is the Earth furthest from the sun? Intuitively, you might think we're furthest away during the freezing cold of winter, but let's see how this elliptical orbit actually plays out in reality.
So, comparing these two key orbital events side by side gives us the answer. Aphelion is the scientific term for when we are furthest from the sun. And get this, that actually happens around early July, specifically July 3rd. Contrast that with perihelion, which is when we are closest to the sun, and that happens right around January 3rd. And because the orbit is elliptical, the Earth's speed actually changes as we travel. It's kind of like a giant slingshot. We move fastest when we're being pulled in closest at perihelion, and slowest when we're coasting furthest away at aphelions. Moving right along to Section 2, the magic 23.5-degree tilt. This right here is the primary reason our planet experiences varying seasons. 66.5 degrees. Absolutely lock this number into your memory for exam day. The Earth doesn't just sit perfectly straight up and down as it travels through space. Instead, its spin axis is tilted at exactly 66.5 degrees relative to the plane of its orbital path around the sun. Now, what's really interesting is the other side of that geometry. If you subtract 66.5 from 90, you get this very famous number, 23.5 degrees. This is the angle between the sun's apparent path, which we call the ecliptic, and the Earth's equator. In the world of celestial navigation, we call this specific, totally vital angle the obliquity of the ecliptic. So let's see how this geometry plays out geographically with an actual exam question. What is the highest latitude at which the sun will reach an altitude of 90 degrees above the horizon at some time during the year? Now, reaching 90 degrees means the sun is dead overhead, right at its absolute zenith. Figuring this out requires a bit of critical thinking about how that 23.5-degree tilt directly dictates the tropics of Cancer and Capricorn. And the answer is exactly 23.5 degrees. Why? Well, because the sun only ever reaches a perfect 90-degree overhead angle between 23.5 degrees north and 23.5 degrees south. It literally passes over every single latitude between those boundaries exactly twice a year, once as it moves north and once as it moves back south. So the crucial takeaway here is this. That specific inclination is the sole reason for our seasonal climate changes and why the duration of day and night shifts throughout the year. Honestly, if our axis wasn't tilted, the sun would just relentlessly bake the equator, and seasons wouldn't even exist. Okay, let's challenge you with another planetary extreme, which is the highest latitude where the sun will rise and set every single day. We just talked about where the sun gets directly overhead, but what about just witnessing a normal, everyday sunrise and sunset? Here's your answer, 66 degrees latitude. Remember that 66.5-degree axis tilt we locked in earlier? Well, above 66.5 degrees north or south, way up in the Arctic and Antarctic circles, the Earth leans so dramatically away from or toward the sun that it literally never sets in the middle of summer and never rises in the dead of winter. Therefore, 66 degrees is the absolute highest latitude option you can select where a normal daily sunrise and sunset still reliably happen.
All right, Section 3, decoding twilight and horizons.
Let's shift our focus a bit closer to the surface and look at some atmospheric phenomena. Fun fact, when you look at a sunrise, you aren't actually seeing exactly what you think you're seeing. Atmospheric refraction causes sunrise to occur earlier and sunset to occur later. Basically, our Earth's atmosphere acts exactly like a giant optical lens. It bends or refracts the sunlight right over the curve of the Earth. That means we visually see the sun hovering above the horizon when, strictly geometrically speaking, it's technically still completely hidden beneath it.
And this atmospheric bending brings us perfectly to a highly testable concept for your exams. Civil twilight is defined by what specific sun altitude? This pops up multiple times in your source materials, so it's absolutely vital to know for aviation and navigation. 6 degrees. That's the magic number. It is strictly from the moment of sunset until the exact moment the sun's center drops to exactly 6 degrees below the sensible or true celestial horizon. Not 5, not 7, exactly 6 degrees. It's basically that period of extended light where you can still confidently do normal outdoor activities without needing any artificial illumination.
Last up, Section 4, Perfecting Cosmic Timekeeping. Let's figure out how we standardize all this massive natural clockwork into something we can actually put on a wristwatch.
Let's bridge the gap between planetary physics and practical human timekeeping with this question. When day length is measured by the apparent sun, does it vary over the year? Think back to what we established about that elliptical orbit and our changing orbital speeds. Does a real, natural solar day actually stay exactly 24 hours all year round?
Actually, it varies wildly. The apparent solar day is governed by the actual true sun in the sky, and because of our elliptical orbit and shifting speeds, that solar day fluctuates anywhere from 23 hours and 44 minutes to 24 hours and 14 minutes. I mean, try running a modern airline schedule on that. You just can't. So, to solve this massive headache, navigators mathematically invented the mean solar day, which is a completely fictitious mean sun that travels at a perfectly constant speed along the equator. That fake sun is what gives us our reliable, perfectly standardized 24-hour day.
Let's anchor ourselves for a second with a universal truth. All heavenly bodies rise in the east and set in the west. But why? Because the Earth continuously rotates on its axis from west to east. If you were floating in space looking down directly from above the North Pole, you'd see us spinning counterclockwise. That west to east spin of the globe is exactly why the sun, the moon, and the stars all appear to travel across our sky in the exact opposite direction, always rising in the east and setting in the west.
Okay, let's talk real-world practical application. The times given in the Air Almanac, those massive, dense tables for sunrise, sunset, and twilight, are all provided in LMT, or local mean time. As a student and a future navigator, what you absolutely need to take away from this is that you can't just read the table and take off. A pilot has to take those LMT tables and apply longitudinal calculations to convert them into UTC, or Universal Time Coordinated, for their specific flight planning.
All right, let's bring it all together. Take a mental screenshot of these 3 points. First, our elliptical orbit means changing orbital speeds, creating aphelion and perihelion. Second, that magic 23.5-degree tilt gives us our seasons, our shifting daylight, and literally creates the tropics. And third, because nature's apparent sun is incredibly messy and fluctuates, we use a mathematically fictitious mean sun to give us our standardized 24-hour time.
To wrap things up, I want to leave you with a final, slightly provocative question to really test your deep understanding of Chapter 1. If the Earth's orbit was a perfect circle and the axis perfectly vertical, how would human navigation and timekeeping change forever? Think about it for a second. We'd have absolutely no seasons. There'd be zero need for a fake mean sun, because the apparent sun would be flawlessly consistent. Every single day would be exactly the same. It really challenges you to truly appreciate our wonderfully imperfect cosmic clockwork and why we navigate the way we do. Keep pondering that, study hard, and I'll catch you in the